So operating cost of a truck is 12 plus X over 6 cents per mile, and the truck travels X miles per hour. If the driver earns $6 per hour, what is the most economical speed to operate the truck on a 400-mile turnpike? Due to construction, the truck can only travel between 35 and 60 miles an hour. So we're dealing with some constraints related to the speed. So that's perfectly fine. So we'll let, well, we don't really have to let it, but it's already been let. X represents miles per hour, so that's going to be the rate of speed, and that needs to be in the interval of 35 to 60. All right, so what we want to know is the most economical speed. Well, if it's going to be economical, then it's going to minimize cost. All right, so minimize the amount of cost. Make a little note. And bless you. I gotta thin down some of my files here because it's starting to lag again. All right, so we have the operating cost. That's dealing with basically the amount of money per mile. So we can address that in a second. And then we're dealing with the driver and how much that individual would earn per hour. So we need some expression that's going to represent in total how many hours he's driven, because our cost we would look at as the operating cost of the truck which we could say is 12 plus X over 6. All right, now the units there, just important to think about, this is money. So in dollars. Bless you. Plus the cost for the driver. All right, so this person is driving, so performing his duties, I suppose, at a rate of $6 per hour. So if we only knew how many hours this person would be on the road, then we would have the cost for the driver in total. All right, so 6 times, I'll just say hours. All right, but the issue is we don't really have any representation of hours, but we do have a relationship that gives that speed is equal to distance over time. Just kind of taking a little old school here. All right. So if we solve it for time, time would be distance over speed. Now, this problem defined speed as X miles per hour. So I can make that substitution. And they told us that the distance is 400 miles, so 400 over X, right? So the hours, quote unquote hours, would be a unit of time. So we can swap out the hours. All right, and so as I astutely pointed out, that since this would be in dollars, where the other one is in actually cents, I mean, I accidentally used the wrong symbol there just out of, I was merely testing to see if you were all paying attention. This would be cents. 2 of those bad boys? Well, it would have to be going 120 miles an hour in order to do that. So this is dollars, so let's make it cents, as clearly anybody would think to do. Multiplied by 400 over X to represent the time. That's again coming from here. So our units are consistent. The only thing that we would have to be careful about, I mean, now that we avoided making a major mistake, because, you know, this didn't happen, but if it did, and I carried through this mistake and got the wrong answer, I'd have to erase like a ton of things. It would suck, you know, like you don't want to deal with that. I mean, it's a good thing that didn't happen. But another thing to keep in mind is you never really know what the phrasing of the question is going to ask in terms of a final answer. So are they going to want the answer back in dollars if they ask for the minimum cost, in which case you might have to convert back. All right, so a lot of things to be careful about in this question, none of which I was careful about. All right, let's try a different technique called the right way. So that's 24 with 4 zeros, because after middle school I stopped caring about what the actual number was called. So 1/6 minus 24 again with 4 zeros, which would take a few syllables to say, I guess. Set it equal to 0. We note that there is a vertical asymptote at x equals 0 for the original. That would also hold over for the first derivative, so I'm not worried about setting my first derivative equal to undefined. If that sounds familiar, that's because I said it before. So 0 equals 1/6 minus, I'll write this as 240 with 3 zeros, or 24 with 4 zeros. Middle school teachers are freaking out right now. Clear out by multiplying by 6x. Squared. All right, so we'll get x squared minus 144 with 4 zeros. There's no way it could be 1,200 miles an hour, so.
It's a fast truck.
Yeah, it's Optimus Prime is what it is.
That's what that is. No.
I'm just going to pretend that it's Monday morning and that these are just Monday mistakes. Yeah, so I put an expression here to represent the operating cost of driving a truck per mile, but never actually stated how many miles the truck would be going, which is kind of an issue, because if it's happening for every mile and it's going for 400 miles,
Yeah, that'll do it.
so this should be multiplied by 400, and so should this. All right. The good news is, I mean, it's slightly good news, is that it's kind of a quick fix, because the 400 multiplied by 12 is still constant through differentiation process, is still going away. All right. 400 times 1/6, I could just carry that through. So 400 times 400 times. All right, at which point we'd get hopefully something more reasonable. And I think I was missing a 0 on this one anyway. I was flabbergasted, as it were. So those would go away. X squared would be 3,600. So X would be, I was about to put an approximate symbol, but it's going to be nice.
60 miles.
A clean 60 miles per hour.
I mean, obviously going the fastest then would be most, well, No. Right? When you get up to like 80 miles an hour, it starts because
Where you're in the car or the truck.
Well, but
but
if
it's
the cost of the truck is
aerodynamics of
constant.
it like uses more.
Oh, because it's hitting more resistance, so it's got to
Well, then you have
crank
to
out
change
more
the
fuel.
That's why
operating cost of
like
the truck.
there was a movement a while ago where they wanted to like change all speed limits to 55 miles per hour because it was like the most environmental.
That's the optimal for
like,
environment.
Yeah, but then you
I
when
mean-
you're using more gas, you're also.
I mean, there's something to that, yeah.
Per hour.
But you know what? There's the 40 mile an hour rule too, where it's I think it's 40 miles an hour.
Like a minimum.
No, it's for air conditioning versus windows. Under 40, windows because the drag is negligible. Once you go over 40, you want air conditioning because the impact of the resistance has more of a result on fuel consumption than the air conditioning would for speeds over 40 miles an hour. So that's this, just with a significant amount of data collection. All right, so yeah, sorry about all those false starts, but that's, I mean, if that's not an indication of why this is a group test tomorrow, I don't know what it is. There's a lot of details in there.
For number 11, if it's speed and density, I just don't know what the second equation is that you need to like create.
Okay, you can take a look. All right, speed of traffic through the Lincoln Tunnel depends on the density of the traffic. So S is the speed in miles per hour. All right, so they're defining variables for us, which is just lovely of them. I always get nervous when that happens. D is the density in vehicles per mile. All right, the unit's probably more important than anything else. All right, because density it's a wonderful word, but it can mean a lot of different things. In this case, it's vehicles per mile, so it's giving you a sense of what you're up against. All right, the relationship between S and D is approximately this. All right, so find the density, all right, that will maximize the hourly flow. All right, so again, density is accounted for in there. So hourly flow.
I got water.
All right, so speed is given, but that's not going to give us the hourly flow within the tunnel. All right, so it's still a speed equals distance over time kind of relationship. All right, so the density part, vehicles per mile, we want to keep that down, and the relationship here is, I think, probably obvious. Where if you have fewer cars in the tunnel, the cars individually can travel at a faster rate. Right? The more cars you include, the more bunched up they're going to be, and the less freedom of movement they're going to have. So that's easy enough. All right, but we know our units here are miles per hour for the speed. What we need is the number of cars per hour. That would be the hourly flow, all right? So we need to come up with some kind of relationship that's going to yield that as a result, all right? So that would be vehicles, to use their terms, all right, because they use that term a couple of times. All right, so the density is given in vehicles per mile, so let's just make a note of that. So just looking at the units, I could say that the number of vehicles would be density times the number of miles. All right, so when we're creating our relationship, I could make a substitution off the bat. density times the number of miles per hour. All right. Now, the issue here is that we don't have, it's not really a significant issue. It's going to clean itself up beautifully in a sec. So you're looking at this, you don't see anywhere where they tell us the number of miles for the Lincoln Tunnel. You don't have to Google it. You know, the number of hours, an hourly flow, so it's per hour, so you might assume 1, but we don't want to go there because we want something that's going to be instantaneous, all right? We do know that miles per hour is the same as saying distance over time, or speed. All right, so what we get from this is the relationship that hourly flow is really density times speed. All right, so I'll represent hourly flow as F would be equal to density times whatever speed is, in this case 42 minus d over 3. All right, so it's the units, I find anyway, the units that drive my thinking. Because there's formulas there's formulas for everything. People do problems like this and then they publish the formulas that they invented it, but really it's the units that drive the development of the formula. All right, if I distribute, F would be equal to 42d minus 1/3 d squared. So now what we're looking at is a relationship between hourly flow and density. So if I optimize this, I'll have what I'm looking for. So, you know, barring any negligence on my part in terms of the units, 42 minus 2/3 d. Now this is continuous and differentiable for all d. Contextually, we're not going to care about it for certain values of d because density is vehicles per mile, so it can't be negative. Zero, I suppose, is possible, and no cars in the tunnel. I don't think I've ever experienced that, because if I experience no other cars in the tunnel, there's still 1 in there, right? And anything over 100, I mean, you're getting towards maybe a traffic jam, all right? So something in the domain is what we're up against, what we're looking for. So 42 minus 2/3 times the density, so 2/3 d equals 42. So d would be 42 times 3/2. So 63. And continuing my theme of never making a mistake ever, this would be vehicles per mile. All right, that would minimize the hourly flow, although, would it minimize? It could maximize, I suppose. You know, while I'm neglecting things, I might as well neglect everything. F double prime would be negative 2/3. That's concave, which of course means concave down, making this a relative max, which is indeed what we were looking for, as I've been saying all along. So 2022 is a pretty easy setup. Rectangle is inscribed under the arch of the curve. Now the curve is a cosine function going from negative pi to pi. So quick sketch with that. Maybe that was too quick. Here's negative pi. And here's pi. All right, cosine wave starts off at its amplitude. Then it hits the hits the midline at the quarter wave point. But since this is a frequency of 1/2, that quarter wave point will be at pi instead of pi over 2. I mean, worst case scenario, if you're ever in a jam, I mean, you don't have to go back to like algebra 2 ways of creating these graphs. Just plug in the negative pi and the positive pi. Just make sure that they give you zeros. All right. What are the dimensions of the rectangle of the largest area, assuming that it's inscribed under the arch? All right, so let's place it under the arch. All right, so I'm going to call this side x. All right, it's a horizontal distance. Now, the vertical part would be y, but they're telling us that y is equal to 4 cosine 1/2 x. All right, so that distance here, that vertical distance, is dependent on whatever x is. All right, and so if x is, for example, pi over 4, I would get the y value associated with that by just plugging the pi over 4 in for this. All right, so that actually is the vertical dimension. Now, I'm looking for area. Area would be the two sides multiplied. X is only that one little piece in the middle, or a half distance. So the whole side would be 2x. So my area model would be 2x multiplied by y, but more specifically, 2x multiplied by 4 cosine 1/2 x.
Couldn't you just decide to make the whole bottom x?
You could, but then this wouldn't be defined by whatever x is, because x is always the distance away from the origin, horizontal. All right, so I'll clean it up a little bit as soon as I get my pen on. So we're looking at 8x cosine 1/2 x. All right, so it's continuous differentiable. All right, cosine function never goes undefined. All right, product rule. First times the derivative of the second, so that would be negative 1/2 sine 1/2 x plus the second function times the derivative of the first would be 8 cosine 1/2 x. So red for the 8, cosine 1/2 x. All right, so this is what we'd be setting equal to 0. So negative 4x sine 1/2 x plus 8 cosine 1/2 x. And if you could solve that without a calculator, good for you. So use graphing calculator to solve for x. Then once you do that,
Can that be an error? That was triangle.
it's not an error. It's just that some of these questions are calculator questions, some of them are non-calculator
But
questions.
you always say that, like, if you always say these problems could be on the non-calculator section. So I thought I should use the calculator.
Okay, so the error would be just to put a little calculator symbol next to the question. I'll do it Ingram style. All right. So then, once you get the value of x, or values, maybe it's multiple, then you would test it in the second derivative. So if you know that you're using the calculator at this point, you would not find the derivative of your messy derivative here, because it'd be power rule all over again. I'm sorry, product rule all over again. You'd use your calculator to just verify that it's going to give you the appropriate sign at that critical value. All right. So that should kind of work itself out at that point. We know how to do this on a calculator? Yes?
Yeah.
You just plug in values.
Plug and shut? Yeah, just make up values for x and hope for the best. No, so one equation is y equals 0, the other is y equals all this stuff. Find the intersection. All right, you could use a 0 function, but I don't like that. It's annoying.
Oh, wait. You said. Okay.
So no? Do it real quick.
Why does that work?
Because
it's 0, because you're just looking for a 0 that's reason why.
Yeah, the 0 function's a pain to use. So I use this technique.
Cardi's way up.
So you would just plug it all in and then do like find the derivative of it and then
And let the derivative function do the magic. Sometimes that run it has trouble because of the numerical approximations involved. So actually find the derivative but then go this route. Domain-wise, we know what the domain is. We created the graph. So negative pi to pi, 0 to 4, create the graph. We're just looking for a couple of zeros. We got them. We're looking for dimensions, so I only want the positive one. Second trace 5. And then just get over to where you think that intersection is and hit enter. So we're getting about 1.72 on the x value. Then you'd figure out y, and then area would be 2x y, which you could figure out based on the solutions to x and y. All right.